Here's another example of a boundary value problem, but this time involving derivatives. So let's find the eigenvalues and eigenfunctions of the differential equation y double prime equals lambda y, but this time the derivatives at 0 and 1 are 0 instead of just a function being 0. And I would like to remind you, eigenvalues means find all the values of lambda for which the differential equation has a non-zero solution. And eigenfunction means those functions, those non-zero functions. Okay, so as usual, let's just find the auxiliary equation. So hopefully you notice that the steps are pretty much exactly the same. So the auxiliary equation is r squared equals lambda. We need to argue in terms of cases. So let's assume lambda is positive. Then lambda is the square of a positive number. Omega squared for some positive omega. And then our auxiliary equation becomes r squared equals lambda equals omega squared, which then gives you r is plus minus omega. And in this case, the solutions are a e to the omega t plus b e to the minus omega t. Now, what we need to do, we need to calculate the derivatives and plug in 0 and 1. So let's calculate y prime of t. So by the chain rule, it's a omega e to the omega t, like r, and minus b omega e to the minus omega t, like whoop. And y prime of 0, it's a omega e to the 0 minus b omega e to the 0, which is r minus whoop. But remember, y prime of 0 is 0. So a omega minus b omega is 0. So a omega equals b omega. Now we want to cancel out omega, which we can because remember, omega is positive. So in fact, you get a equals b. In which case, our solution so far is a e to the omega t plus, not b e to the minus omega t, but a e to the minus omega t, since a is b. Okay, and now we want to use the fact that y prime of 1 equals 0. So we have a formula for y prime. So a omega e to the omega times 1. And then, so minus b omega, but b is a. So minus a omega e to the minus omega times 1 equals 0. And so we get a omega e to the omega equals a omega e to the minus omega. And there are a lot of cancellations here because, once again, omega is non-zero. And moreover, a is non-zero because otherwise y would be 0. It would be 0e plus 0e. And a is non-zero. And so in the end, what we get here is e to the omega equals e to the minus omega, e to the minus omega, then take logs, you get omega is minus omega, and this gives you omega is 0, which once again is a contradiction because then lambda is omega squared, which is 0 squared, and that's 0. Because remember, we assumed lambda was positive. So what is the conclusion? In this case, no non-zero solutions. No problem though, because, well, let's look at the other cases. So case 2, let's look at lambda equals 0. In this case, the auxiliary equation is r squared equals lambda equals 0. So r equals 0, and let's repeat it twice. Twice. Go once, go twice. So, and we then get, again, y of t is a e to the 0t, so a plus bt e to the 0t, so just bt. And remember, we need to calculate y prime of 0 and y prime of 1. So y prime of t here is b, and then y prime of 0 is b, which is 0. So in particular, b equals 0. In which case, y of t is a plus 0t. So y of t is a, which you will see later why I do this, but we can write this as a times 1. So it's really a multiple of 1. So keep this in mind. However, what happens when we take this constant function and take the derivative at 1? Well, in this case, the derivative is automatically 0, meaning that the second boundary condition is automatically satisfied. So then, in this case, y prime of 1 equals 0 is automatically satisfied. Contradiction? No. In fact, we found another eigenfunction, namely multiples of the function 1. So conclusion. So lambda equals 0 is an eigenvalue. So it's a legit value of this problem. And what is the eigenfunction? Function. So not a, but again, multiples of which function? Multiples of the function. So keep this in mind. I promise it'll be less confusing after case 3, because something beautiful will happen. Okay, very good. We can put this in our basket. And let's continue with case 3. So let's do lambda negative. And in this case, lambda is minus omega squared, where omega is a positive number. And the auxiliary equation is is r squared equals lambda is minus omega squared. So r is plus or minus omega I, which once again gives you cosines and sines. So y of t is a cosine of omega t plus b sine of omega t. Now we want to calculate the derivative. So y prime of t is, in this case, minus r sine of omega t plus v cosine of omega t. And let's calculate y prime of 0. So minus r sine of 0 plus v cosine of 0. But again, sine of 0 is 0, cosine of 0 is 1. So we get b omega. But remember, y prime of 0 is 0. So b omega is 0. equals 0. And then remember, omega is positive, so we can divide by omega, and we end up getting b equals 0. And let's go back to our function y, which is a cosine plus b sine. Since b is 0, we then end up getting y is a multiple of cosine of omega t, which again I will box because this will be useful in a second. Okay, and now we just need to find y prime. Or I guess we need to figure out when y prime of 1 is 0. Now, remember, we have a formula for y prime of t, but with b equals 0. So in this case, minus a omega sine of omega 1 equals 0. And once again, we can cancel out omega since it's positive. We can also cancel out a since it's non-zero. A is non-zero because if a were 0, we would have the 0 solution. And so what we end up getting is sine of omega. Omega equals 0. And once again, who is here to save the day? Peyam. So in this case, omega is Peyam, where, again, we want omega to be positive, so m is from 1 to 3. So always, if you wondering when the starting point is, always figure out when omega is positive. And in this case, what we get is lambda is minus omega squared, which is minus Peyam squared, and our function y of t. So go back to the box answer here. This time is a cosine of omega t, or without the constant cosine of omega t, which is cosine, in this case, of Peyam t. Because omega is Peyam. But here is the beautiful thing. So that was case 3. And I would like to remind you, in case 2, we found lambda is 0 and y is 1. Now, look at this formula in case 3 and see what happens if you plug in m equals 0. In other words, if you let, so note, if you let m equals 0 in case 3, then, well, lambda is minus pi 0 squared, which is 0, and y is cosine pi 0 t, which is cosine 0, which is 1, which includes case 2. I mean, wow, when are things that nice in math? Very rarely, but here we can have nice things. Case 2. So once again, strictly speaking, case 3 starts with m equals 1. But if you also let m equals 0, this includes case 2. So really the epic conclusion is the following. So first of all, the eigenvalues is lambda equals minus pi m squared, where m starts from 0. So 0 minus pi squared minus 4 pi squared, etc., etc. So m from 0, 1, 2, 3. It's important that we start at 0 here. And the eigenfunctions here are cosines. So y is cosine pi mt, which here is 1, cosine pi t, cosine 2 pi t, etc., etc. Where once again, we start at 0. 0, 2. So the moral of the story is sometimes case 2 works, sometimes it doesn't. But the nice thing is there will always be this nice simplification in the end. And last but not least, in the lecture notes, there's also a next example that I invite you to check out.